Hello everyone, welcome to the Waveguides tutorial. So our goal for today's simulation is to simulate a rectangular waveguide with particular geometrical parameters around its cutoff frequency, which is 5 gigahertz. Okay, so we aim to demonstrate that below 5 gigahertz, below cutoff frequency, the waveguide doesn't support waveguiding modes, but above cutoff frequency it does. Okay, so as usual, we open ANSYS desktop, and right-clicking the project, we insert the HFSS design. So HFSS here stands for High Frequency Simulation Solver. We create the project. Our waveguide will be arranged along z-axis. We draw an arbitrary brick, which will be our waveguide. Okay. And change its size, change its dimensions. X size parameterizes A. Give it a size 30 millimeters. So it will be the width of our waveguide. Y size B. It's a height of our waveguide. Let's put it 15 millimeters. And the Z size, which is the length of our waveguide, 100 millimeters. So this is our brick. It's too large to fit. We can click fit all to see the entire box. Okay, so by default, this box is made of vacuum. So there are different ways to create a rectangular waveguide in HFSS. We will be using the simplest one, basically using the fact that by default, ANSYS assumes that the exterior area around the body is a perfect electric conductor. Okay, so we assume that our waveguide is made of perfect electric conductors, so we don't need to draw the walls for this waveguide. And this box will be the inner area of my waveguide. So I'm changing the material to just air. Make it transparent. First, second, so we created the box, right? It's not important, but we can put the boundary conditions of perfect electric wall. So in the selection mode, I choose phase and select all the walls except for the these phases, right? And right click and then assign boundary perfect E. It's a boundary condition that mimics the condition of the perfect metal. Okay, so now we need to put the excitation ports. I start from this, selecting this face, right click and assign excitation wave port. in this dialog window, I click on the integration line and create a new line. So this line will be representing the polarization of my waveguiding mode. So I draw this line here. Okay. Then next and finish. If I go to the project window, and I will see that this waveguiding port is shown up here in excitation. So this is my first port. Similarly, I create the second port. Both ports are created. Let's change this box name to Waveguide. So the next step is to create the analysis type. Right-click analysis, then add solution setup and advanced. So in here, we simulate our waveguide around 5 gigahertz. Let us increase this number of passes to at least 10. And click OK. In the pop-up window for the frequency sweep, we change the starting frequency to let's say 3 gigahertz and ending to 7 gigahertz. I change linear count to linear step and change the step of my frequency sweep to 0.1 gigahertz. Okay. So clicking preview, I can show up the list of the frequencies at which my project will be simulated here. And this is important. I also enable safe fields for all these frequencies. This is important. And okay. So my design is created, my excitation is created. I can validate my project. It looks good. And I mean, if needed, we can also change the mesh, for example, improve it a little bit. And then after setting the mesh, analyze all. All right, simulation is done. So the first step we can do, we can show the field results. To do so, I select the waveguide, and as usual, I plot the fields, electric field in vector form. So by default, it says 5 gigahertz for the frequency. We need to change this to the 3 gigahertz by going to the sweep, which will enable us to select the frequency. Let's do 4 gigahertz. Vector field, done. So we see that in this case, for 4 gigahertz, the electric field is strong in the input here, but then it is vanishing, right? We can also animate this field distribution by going to the field and selecting animate from 0 up to 350, step 35. So you see that the field doesn't propagate. So it localized in the input, but then it quickly decays. All right, let us check the field in this waveguide at 6 gigahertz. Sweep, 6 gigahertz. So you see it's completely different. Again, I can animate this field. And as a result, you see that now, in this case, the field is indeed propagating. So we conclude that somewhere between 4 and 6 gigahertz, this particular waveguide gets a cutoff frequency. To reveal that cutoff frequency, let us go to the results, right click and select create rectangular plot. And then here by default, it provides this S parameters calculation. We select, for example, S21 in dB. Create. Indeed, below, so S21 or S12 is a transmission coefficient, meaning that 0 dB means the input of 1 watt to the system freely propagates above 5 gigahertz, but quickly attenuates and reflects back to the port below 5 gigahertz. Okay, so indeed this 5 gigahertz is the cutoff frequency of our waveguide. I also want to see the magnitude of the field. For example, to plot the magnitude in the bulk of this waveguide, I can draw the rectangle in the XZ plane, somewhere in the middle. Adding this element doesn't change the project because this element is auxiliary. It's not a material object. Again, I can make this object transparent and selecting this object, I can plot the electric field, magnitude of electric field. At 4 gigahertz. So you see, the field doesn't propagate. And above cutoff. So in this case, the field indeed propagates. So finally, let us see the field in the transversal direction, transverse plane. Make it transparent. And plot vectoral electric field. It was 5. Now let us do above. So you see, this is indeed the fundamental TE 1-0 mode. 1 because it is one complete oscillation of the field in the x direction, and no variation of field in the y direction. So for your report, you will need to get this as parameter result as 1, 2 parameter to demonstrate that the cutoff frequency is indeed 5 gigahertz. Compare this result with the analytical calculation via the formula. Discuss or explain any discrepancy, and provide the fields below cutoff and above cutoff, and discuss the observed behavior. Thank you for your attention.